The internet feels invisible. A message leaves your phone. A payment crosses a border. A video appears on your screen. And everything seems to happen in the air, instantly, silently, without friction. But the internet is not weightless. It is not floating above the planet. It is not a cloud. The internet is physical. And some of the most important pieces of that physical system are lying thousands of meters beneath the ocean, across the seabed, between continents, inside a network of glass fibers thinner than a human hair. These cables carry the world's data, financial transactions, cloud services, government communications, corporate systems, video calls, search queries, artificial intelligence workloads, and billions of private messages, every day, across the oceans. The modern global economy depends on them, and yet, most people never see them. They are buried beneath the water, protected by geography, invisible to consumers, and strategically important to almost every major power on Earth. This is the hidden infrastructure of the internet, not the websites, not the applications, not the platforms, the network beneath them. Because the digital economy may appear to exist in cyberspace, but its most important pathways are made of glass, and they run through the ocean.
The modern economy is built on communication, but communication requires infrastructure. For decades, that infrastructure has increasingly moved beneath the sea. Submarine communication cables connect the world's continents. They form a vast underwater network, a hidden nervous system for global civilization. The network connects major financial centers, cloud computing infrastructure, technology companies, governments, telecommunications providers, and billions of users. When data travels from one continent to another, it often travels through the ocean, not through satellites, not through some invisible digital dimension, through physical cables. The reason is simple. The amount of data moving across the world is enormous. Modern economies require constant, high-capacity communication. Financial markets, cloud platforms, video streaming, enterprise software, artificial intelligence, international commerce. All of them generate massive flows of information, and the most efficient way to move that information across oceans is through fiber optic infrastructure. Inside the cable, information travels as light. A message becomes a signal becomes a pulse, and that pulse travels through glass at extraordinary speed, across thousands of kilometers. The result is a strange contradiction. The most advanced digital economy in human history still depends on a physical network that can be damaged by geography, anchors, fishing equipment, natural disasters, and human conflict. The internet may be global, but its infrastructure is not infinite. It follows routes, it enters specific locations, and it depends on physical points that can be identified. That creates something every system eventually creates, a choke point.
A submarine cable is not simply a wire dropped into the ocean. It is an engineered system. At the center are optical fibers, extremely thin strands of glass. Around them are layers of protection, strength members, insulation, water barriers, and in some areas, heavy armor. The cable must survive an environment that is almost completely hostile to human infrastructure, pressure, movement, temperature, seafloor terrain, and thousands of kilometers of distance. In deep water, the cable can rest directly on the seabed. In shallower waters, the risks increase. Ships operate above it. Fishing equipment moves through the area. Anchors can drag across the ocean floor. So cables may require additional protection. The route itself is carefully planned. The cable cannot simply travel in a straight line. It must navigate geography, avoid certain underwater terrain, connect to specific coastal locations, and arrive at landing stations. These landing stations are critical. They are where the underwater network connects to terrestrial networks. The ocean ends, the digital infrastructure continues. And this creates a structural vulnerability. The cable may travel across thousands of kilometers, but the network must eventually come ashore. The entire global system therefore contains a paradox. The infrastructure is distributed across oceans, but the connection points are concentrated on land. The network is fast, the access points are not. And whenever a distributed system depends on concentrated points, those points become strategically important. Imagine a highway crossing an entire continent. Now imagine that every vehicle on that highway must pass through one gate. That is the logic of a cable landing station. The cable may travel thousands of kilometers beneath the ocean, but eventually, it must connect to the network on land. That connection happens at a limited number of locations, and those locations matter. A landing station is more than a building. It is a transition point. The underwater network meets the terrestrial network. International data enters a national infrastructure system. The physical ocean becomes the digital economy, and the architecture suddenly becomes concentrated. This creates a strategic question. What happens if a cable is damaged at sea? The answer may depend on redundancy. If other cables exist, traffic can be redirected. If alternative routes are available, the disruption may be absorbed. But redundancy is not the same as invulnerability. A network can have multiple cables and still have concentrated geography. Several cables may arrive near the same coastline. Several routes may connect the same major economic centers. Several systems may depend on the same infrastructure corridor. This creates a hidden form of risk. The internet can look decentralized from the perspective of the user, but the physical infrastructure may be concentrated in ways most users never see. The network does not need to be completely destroyed to experience disruption. A critical connection only needs to become unavailable. And suddenly, the invisible network becomes visible. The loading stops. The payment fails. The service slows. The connection disappears. A physical event beneath the ocean becomes a digital event on a screen.
For centuries, the ocean was a battlefield for ships. Today, it is also a battlefield for infrastructure. The seabed contains pipelines, energy systems, communication networks, and data infrastructure. The cables that connect the global internet pass through international waters, near coastlines, across strategic regions, and between nations competing for economic and technological influence. This creates a new category of geopolitical infrastructure. A cable is not a military base, it is not a weapon system, but it can become strategically important because modern societies depend on communication. Financial markets require connectivity, governments require connectivity, military systems require connectivity, cloud platforms require connectivity. The more dependent the world becomes on digital communication, the more important the physical network becomes. This creates an unusual form of power. A country does not need to control the entire internet. It may only need influence over critical routes. A company does not need to own every cable. It may only need to control the technology, financing, or infrastructure behind key connections. A disruption does not need to destroy the entire network. It may only need to affect a critical corridor. This is how infrastructure becomes geopolitics. The cable itself may be made of glass, but the system around it contains national security, economic power, corporate competition, and strategic leverage. The ocean floor has become part of the architecture of global power.
A single cable can be vulnerable, but the internet is not built around a single cable. It is built around networks, multiple routes, multiple systems, multiple connections. This is redundancy.
and redundancy is one of the most important principles in infrastructure design. If one route fails, traffic can move through another. If one connection is damaged, the network may reroute. If one region experiences disruption, alternative infrastructure may absorb the demand. This is why the global internet can continue operating even when individual cables fail. The system is designed around failure. But there is a difference between surviving failure and being immune to failure. Redundancy has limits. Not every route is equally fast. Not every cable has the same capacity. Not every region has the same number of alternatives. And not every connection can be replaced instantly. There is also a question of scale. Data demand continues to grow. Cloud computing continues to expand. Artificial intelligence is creating new demand for global connectivity. More data centers are being built. More services are moving across borders. More businesses depend on international infrastructure. The system therefore has a problem. Demand is rising. The network is expanding, but the physical routes remain limited by geography. There are only so many places where cables can cross oceans, only so many coastal landing points, only so many paths that are commercially and technically viable. This creates an infrastructure paradox. The network becomes more redundant, while the world becomes more dependent on it. And as dependence increases, the value of each critical connection rises.
The internet does not only carry conversations, it carries money. Financial markets operate across borders, banks communicate with one another, payment systems exchange information, companies move capital, investors react to events, and in some areas of finance, speed itself becomes valuable. A faster connection can mean faster information. Faster information can mean faster decisions, and faster decisions can create economic advantage. This is why network infrastructure has become deeply connected to financial power. A cable is not simply transporting data, it is transporting information that can influence markets. The physical route between financial centers therefore becomes economically important. Distance matters, latency matters, reliability matters. The architecture of the network becomes part of the architecture of finance. This creates a strange reality. The most advanced financial systems in the world may depend on physical infrastructure that can be damaged by a ship's anchor. The world's most sophisticated markets still require cables beneath the ocean. The most complex algorithms still require a physical pathway. The most advanced digital economy still depends on geography. This is a recurring pattern in modern technology. The surface becomes more abstract, the underlying infrastructure becomes more physical. The user sees an instant transaction. The system sees servers, fiber, power, networks, and cables. Every digital transaction has a physical architecture, and the more valuable the transaction, the more valuable the architecture carrying it.
The internet feels like a public space. Anyone can access it. Anyone can publish. Anyone can communicate. But the infrastructure beneath the internet is not owned by everyone. It is built, financed, operated, and maintained by specific organizations. Telecommunications companies, technology companies, cloud providers, infrastructure investors, and in some cases, governments. This changes the economics of the network. The public experiences the internet as a service, but the infrastructure underneath it is an asset, a physical asset, with construction costs, maintenance costs, capacity constraints, and strategic value. Companies that control critical infrastructure can influence how data moves. They can invest in new routes, build additional capacity, connect new markets, and shape the geography of the digital economy. This does not mean one company owns the entire internet. The system is far too large for that. But power does not require total ownership. It can come from controlling important layers: a critical route, a major landing station, a high-capacity connection, a strategic geographic corridor, or the technology required to build and operate the infrastructure. This is the same pattern we see across the modern economy. Power concentrates around dependencies, and the internet is no exception. The network may be open to billions of users, but the physical architecture that makes the network possible is controlled by a much smaller number of actors.
The next phase of the internet will not be defined only by software. It will also be defined by geography. Where should new cables be built? Which continents should they connect? Which routes offer the lowest latency? Which regions are growing fastest? Which countries want greater control over their digital infrastructure? These questions are becoming increasingly important. The global economy is becoming more dependent on data. Artificial intelligence is expanding. Cloud computing is spreading. Digital services are reaching new markets. And every new digital economy requires physical connectivity. This creates competition over routes. A new cable can connect a growing market, reduce dependence on an existing corridor, create a faster connection between financial centers, or shift the strategic balance of a region. The cable itself may be invisible to most people, but its route can shape economic power. Infrastructure creates geography. Geography creates access. Access creates opportunity, and opportunity creates wealth. This is why the future of the internet will increasingly involve a race beneath the ocean. Not a race for users, a race for routes. Not a race for attention, a race for capacity. Not a race to build the most popular application, a race to control the infrastructure through which the applications must communicate. The companies that build the visible internet may change, the platforms may rise and fall, but the physical network beneath them will remain. And whoever builds the next generation of that network will help determine where the next generation of digital power flows.
The internet has changed how humanity thinks about distance. A message can cross an ocean in seconds. A payment can move between continents. A company can serve customers on the other side of the planet. An AI system can communicate with infrastructure thousands of kilometers away. The world feels connected. But connection requires architecture, and architecture creates dependencies. Beneath the digital economy, there is a physical network. Glass, light, power, geography, and the ocean. The cables running across the seabed are not simply infrastructure. They are the hidden pathways of global commerce. They connect economies. They connect markets, they connect governments, they connect people, and they create a system that is both distributed and concentrated, redundant and vulnerable, global and deeply physical. This is the paradox of the modern internet. The more invisible the experience becomes, the more important the infrastructure beneath it becomes. The cloud still needs data centers. Data centers still need power. Networks still need fiber. And continents still need cables. Invisible systems create visible wealth. The digital economy has not escaped the physical world. It has simply hidden the physical world beneath a layer of software. And that is where the architecture of power begins. Because whoever controls the visible platform may control the user, but whoever controls the infrastructure beneath the platform may control the system itself. The next time a message crosses an ocean, remember what is really happening. Your data is not floating through the sky. It is traveling through a physical architecture, across a planet, through glass, underwater, along routes that can be mapped, protected, invested in, competed over, and, in the right circumstances, disrupted. The internet may be global, but its pathways are not infinite. They have geography, they have owners, they have bottlenecks, and they have value. Because in the modern economy, the most powerful infrastructure is often the infrastructure nobody sees. And sometimes, the most important network on Earth is the one running beneath it. Nexera, decoding systems, architecting wealth.